The space elevator. You probably heard of it. It's one of those concepts that feels like it's straight out of science fiction. But here's the wild part. It's actually completely grounded in real established physics. So, what would it actually take to build one?
I mean, think about that for a second. Right now, the only way we get to space is by strapping ourselves to a giant, controlled explosion. It's violent, it's inefficient, it's rocket science. The space elevator, though, it promises something completely different. A quiet, clean, maybe even peaceful electric ride up a ribbon right into the cosmos. It's elegance versus brute force.
And that's the big question, isn't it? If the laws of physics are totally cool with it, what's the holdup? Well, as we're about to see, this isn't a science problem at all. It is, quite possibly, one of the most colossal engineering challenges humanity has ever even dreamed up. To really get why this is so hard, we first have to wrap our heads around the sheer, mind-boggling scale of this thing. We're not talking about a tall tower, we're talking about building a structure on a planetary level. Okay, so you know geostationary orbit, right? It's where our big communications satellites hang out, about 36,000 kilometers up. Well, for the space elevator's ribbon to stay taut, held in place by the Earth's spin, it can't just stop there. It has to go way, way further, all the way out to 100,000 kilometers. That is over a quarter of the way to the moon. This isn't just a long cable, it's a piece of planetary engineering. So, how in the world do you build something that long? Well, that question leads us directly to what is, without a doubt, the single biggest showstopper: finding a material that can even exist at that length without just snapping under its own incredible weight. The magic number here, the thing engineers are obsessed with, is called specific strength. And it's not just about raw power, how hard you can pull on it. It's about how strong a material is for its weight. Because when you have a 100,000-kilometer ribbon trying to hold itself up against gravity, that strength-to-weight ratio is literally everything. And here's the brutal reality. None of our best mass-produced materials even get in the same ballpark. The best steel we can make? Nope, not even close. High-tech stuff like Kevlar or Xylon? Still not strong enough. The only things that work, at least on paper, are these almost mythical materials like carbon nanotubes. And that's the catch, right? In a lab, a single, perfect nanotube is strong enough. But in the real world, we have no way of making kilometers of the stuff without a single flaw. And this is where the cruel math of the weakest link comes in. Over a 100,000-kilometer-long ribbon, you don't just have a chance of a flaw. You have a statistical certainty of one. Thousands of them. And even one single microscopic imperfection could be the spot where the entire structure catastrophically fails. We don't just need a strong material. We need an impossibly perfect one, produced on an industrial scale. And we're just not there yet. But, okay, let's just pretend for a minute. Let's say we wave a magic wand and we have the perfect material. Well, the challenges are just getting started. That perfect ribbon would still have to survive a constant, non-stop gauntlet of planetary-scale threats. From the moment it's anchored, this thing would be constantly pulled and pushed by forces. Down low, you've got hurricanes and the jet stream twisting it. It would literally expand and contract by kilometers as it heats up in the day and freezes at night. Every single climber crawling up would send shudders and vibrations down its entire length. It's less like a static cable and more like a planet-sized violin string, constantly in danger of vibrating itself to pieces if you don't actively manage it. And then there's the environment itself. At the bottom, you've got corrosive salt spray from the ocean. Go up a bit, you've got radiation and atomic oxygen that literally eats away at materials. But the real potential killer? Micrometeoroids and space debris. Even a tiny fleck of paint moving at orbital velocity has enough energy to sever fibers and start a catastrophic failure. It's a shooting gallery up there. So we've got the material problem and the gauntlet of environmental threats. But beyond all that, there's a whole other layer of massive systems-level challenges, the kind of stuff you might not think about at first, but that are just as hard to solve. For starters, how do you power a climber for a journey that could take over a week? You can't just pack enough batteries. They would weigh way too much. The best bet is probably beaming power from the ground using high-powered lasers or microwaves. But that means building multi-megawatt transmitters and hitting a moving target the size of a car from thousands of kilometers away, through the atmosphere. That system, all by itself, is a monumental engineering project. And how do you even build the thing in the first place? You can't build it from the ground up. The leading idea is to actually unspool a very thin seed ribbon from a satellite in orbit down to a floating platform in the ocean. Then, you'd send up hundreds and hundreds of robotic climbers, one after another, each one adding another layer to slowly make the ribbon thicker and stronger. It's an incredibly delicate and vulnerable process.
And finally, you get to the human hurdles. Forget the physics for a second. We're talking capital costs in the hundreds of billions, maybe even trillions of dollars. We need entirely new international laws and treaties for a structure that passes through every nation's airspace. And then you have to ask the really hard questions. Who owns it? Who insures it? And who's liable if something goes horribly wrong? These political questions are just as tough as any of the engineering ones. Okay, I know. After hearing all of that, it probably sounds completely and totally impossible. But remember the word in our title, yet. These are all, at their core, engineering problems. And if there's one thing engineers love, it's a seemingly impossible problem. There is a path forward. And that path might not even start on Earth. A lunar elevator could be the perfect stepping stone. Think about it. The moon has only 1/6 of Earth's gravity, and basically no atmosphere. That means the material requirements are way, way lower, maybe even within reach of materials we could make today. It'd be the perfect place to test out the technologies, like power beaming and robotic maintenance, in a much more forgiving environment.
So what's the actual to-do list for an Earth elevator? Well, it's not about waiting for one single magic breakthrough. It's a whole series of huge advances we need to make. We need to master making flawless, ultra-strong materials at an industrial scale. We need to get serious about cleaning up all the space junk in orbit. We need swarms of autonomous repair bots. We need to perfect that power beaming technology. Every single item on this list is a massive goal, for sure, but none of them are actually impossible.
And that's really what it all boils down to. The space elevator isn't waiting for some new discovery in theoretical physics. The physics is sound. It's waiting for us. It's a benchmark for our future abilities as engineers and builders. So the question isn't if physics will let us build it. The question is, when will our competence finally be ready to take on the challenge?